Hello, welcome to the sixth lecture for chapter 7 of Mathematics Class 11, Binomial Theorem. So, till the last class, even before that, we had seen what are binomial expansions. Okay, so binomial expansion, that is like when there is a mathematical expression given with two values or variables, and either their sum or their difference is um, it is expressed in the power. Okay, the whole term is then expressed in, like, we might have to find their value when they are raised to some index. Okay, so the binomial theorem that we had actually proved was we proved that the binomial theorem for any positive integer n, it can be given as a plus b raised to n. So this is the binomial term, and we will be expanding with respect to the power of index that is given. So that can be written as a n c0 a n b0 plus n c1 a n minus 1 b1 plus c2 a n minus 2 b2 plus just a general term, any of the general terms in between, n minus r b r, and the last term of the expansion ncn a raised to n, or you can just write it 0 and b raised to n. Okay, so this is what we have proved, that for any positive integer, okay, any value which is a positive integer for n, this expansion is true. Okay, so now there are a few observations that we will make, based on this. So the first observation, okay, so observations that we can even use when we are trying to, solve examples. The first observation that we can make is that something that we have already discussed previously. Okay, so over here the first one that we can see, that all this entire expansion is kind of a sum of different kinds of terms. Okay, so it's a sum of different terms. So there is another way that you can express binomial expansion. So that expression can be written as, okay, binomial expansion can be represented can be represented as the notation summation. Okay, summation, that means it's a sum of all the terms. Okay, summation of the expressions a n c k a n minus k b k, where k is going from 0 to n. Okay, so if you express it in this form, this again, it means, this summation, this notation is actually a way to represent this entire expansion itself. Okay, so over here now you can see that we are not using r as the changing variable. We are using k over here. So in that manner, when you write n c n a raised to 0 and b raised to n, can actually mean this similar thing as n c n a n minus n. Okay, so when your k is your n, okay, so this means the same thing. Okay, and this again will be 1, which is also equal to whenever you have, if you have b raised to 0. Okay, so the first term, in the first term, you can say that when a is raised to n, b is raised to 0. Okay, so b raised to 0 is 1 again. So this is something that we observe. Okay, so therefore, you can write that a plus b raised to n can be written in the form of a summation over k going from 0 to n. Then we are summing the term nck a n minus k b raised to k. Okay, so this is the first observation. Now the second observation that we see that all the coefficients, okay, NCR are the coefficients of all the terms of the expansion, and they are known as binomial coefficients. Okay, so there is a term that we use for all these coefficients, your NC0, NC1. Okay, so they are all called binomial coefficients. So you all NC0, NC1, if your n is equals to 2, then your 2, sorry, 2C0, 2C1, and 2C2. All of these are called binomial coefficients. Okay, so this is again an observation, or kind of a statement that we can see. Now the next one is your third. So over here, this is something that we have spoken about even before when we were just dealing with binomial expansions. The rules that are followed when you are kind of evaluating such binomial expansions, that with for for the expansion of a plus b the whole raised to n, the total number of terms of expansion will be n plus 1. Okay, so this is something that we have already seen before. So if you have, say, n c r a n minus 1 b r, so in this relation, okay, so we always will have t r plus 1. Okay, so this is a general term. So anytime you take 1 r, the related term is going to be 1 more than that. Okay, so therefore your total number of terms will always be n plus 1. Okay, so t total, okay, will always be n plus 1. So if it will always be, the last term will always be t n plus 1. Okay, last term. And t0, okay, because you will have t0, okay, so that is going to be your t1, actually, your first term will always have the coefficient where your r is going to be 1. No, sorry, r is going to be 0. Okay, r will be 0 at that point of time. Okay, so this is something that we have already seen before when we were solving examples and when we had started the binomial expansion. Now, the fourth observation is that while expanding a plus b the whole raised to n, okay, the index of A decreases by 1. Okay, so this is something we saw. So in the first term, okay, so T1, in the first term, we start with n as the index of index of A. Okay, so maybe you can think of it as A raised to x. Okay, where your x will be n. Okay, and then when you have the next term, okay, so in the T2, you will have x, say -1. Okay, so your power of index goes, it actually decreases by 1. So over here, you will have a n minus 1. Okay, so this is what we have always seen, that this pattern is followed. Okay, and all the way up to when you have the last term, so that is t n plus 1. Okay, because obviously we know that the last term will be, one more than the n that we have. So in the last term, you will have x minus, actually it will be your n. So this will be a n minus n, and this will be a raised to 0. Okay, so this is what we see for A. While the index of B increases by 1. Okay, so in your first term, you will have, say, B raised to y. Okay, so y actually starts with 0. Okay, because why this has to be followed, we will see in the next observation. But we have to always keep in mind that the index of B will start with 0. Okay, in the first term. So in T2, okay, in the second term, you will have B y plus 1. Okay, so this is what we see. Now your y in the start was 0. Okay, so that would be your b raised to 1. Okay, and similarly in the last term, okay, t n plus 1, you will have by plus n. Okay, because by the last term, okay, by the n plus 1 term, okay, you are going to reach by increasing by 1 every term. If you keep increasing the index of b by 1, you will reach the point where you will get n as the index itself. Okay, so b would be actually 0. Okay, we were considering the starting index, the first term index for b as 0. So this will be as b raised to n. Okay, so this is the way that it follows. And then the last one, okay, this again we have seen before, that in the expansion of a plus b the whole raised to n, sum of indices of a and b should be n for all terms. Okay, for all the terms of the expansion, this rule has to be followed. Okay, so in the first term, when say your a is raised to n, okay, so for the sum, okay, so your total, the sum of the index, okay, the indices of a and b should be n itself. Okay, so if a is already raised to n, so this has to be 0, so that n plus 0 would be n. Similarly, in your second term, okay, so in your second term you have a n minus 1. Okay, so what would be b? So in for addition, okay, so n minus 1, and something plus something will have to be n again. Okay, so this has to be 0. Okay, so this -1 and plus something will have to be 0, so that is 1 itself. Okay, so again this is being followed. So for every term, okay, for every term, your sum of indices should actually turn out it will turn out to be n plus 0 is equals to n. So n will always be there, okay, with respect to the index of a. Okay, you have n minus 1, n minus 2. Okay, so whatever is the remaining, okay, so that has to be, plus 0, and then you will get n. So these are few of the observations that we see when we have, proven that binomial theorem exists for any positive integer n. Okay, when we are trying to expand expression, say a sum of two values or sum of two variables or one value, one variable, when raised to the power of that positive integer. Okay. So these are few of the noteworthy observations that we also use when we are trying to solve sums. So let's see an example where we use, one such observation. Okay, so you have, the question is that x is equals to MC1 plus 2 MC plus 3 MC3 all the way up to, say, 10 C 10 the whole raised to 12. Okay, where 10 CR, okay, is for R. Okay, so for R will keep is varying for all the terms that is there are the binomial coefficients. Okay, with R, going from 1 to all the way up to 10. Okay, then find the value of 1 upon 1430x. Okay, so this is what we have been asked. Okay, so this is kind of a, series of some terms. Okay, and these 10C1, 10C2, 10C3, all the way up to 10C10, these are binomial coefficients. Okay, so over here, when we try to simplify or evaluate what x will be, we can see that since all of these are sums. Okay, and also if you see each of the term, okay, of x, you can see that there is when you have 10C1, whatever your r is over here. Okay, so all of these binomial coefficients are in the form of 10CR. So whatever your r is being taken, that is also multiplied outside the bracket. Okay, so over here this is 1 into 10C1. Okay, and over here you have 2 into 10C2 the whole square. Okay, so this is where you can see. So this actually can be written in the form of that summation notation, and you will have r is equals to 1, going from 1 to 10, and this can be written. Okay, so the entire this expansion or this entire expression can be shortened and written as this. Okay, so you whatever r you take, so that r is also multiplied to the square of this coefficient. So this then you can simplify further and write then r into 10CR into 10CR. Okay, now we will not do the entire expansion. Okay, so we will first try to get it down to as as simplified as possible. Okay, now there are a few things we have to remember, that when NC of R is there, okay, you can write it in different forms also. Okay, so what kind of form that we can write is that when we solve for say NCR, okay, so you can write it in the form of n factorial upon R factorial n minus R factorial. Okay, so if you kind of try to expand in the factorial form, you can write this as n into n minus 1 factorial. Okay, and the bottom part you can write as r into r minus 1 factorial. Okay, multiplied by, now if you have n minus r. Okay, so similarly as n factorial can be written as n into n minus 1, so this can be written as n minus r. Okay, multiplied by, now your n also decreases by 1 over here. Okay, so you have n minus r, and your r will also kind of actually become plus 1. Okay, because if you try to see, if suppose this was supposed to be 3 minus 2 factorial, or maybe take something else, like 5 minus 2 factorial. Okay, so that would be 3 factorial. Okay, so then if you write 3 into 2, so to get this 2, you will have to increase your r by 1. Okay, so 5 minus 3 would then become your other if you expand it, if you actually write all these values in form of n minus r. Okay, so that's a bit kind of the logic that goes. So this you can then write n minus r plus 1 and then n minus 1 again. Okay, so this way you can kind of keep going. But what in turn this actually can be written in the form is n by r. Now the other parts you can actually get it into the combination part. Okay, if you take out n and r, so the rest part, if you take say n minus 1 factorial, okay, upon r minus 1 factorial. Okay, and then you try to get all the other also in the factorial form. So what you get is n minus 1 c r minus 1. Okay, so you can write NCR in terms of n by r, n minus 1 cr minus 1. So similarly, then your x can become, okay, then we can turn one of these terms and we can write it in this form. So what that would lead you to is summation over r going from 1 to n. Okay, so you have r multiplied by 10 cr multiplied by 10 by r, and over here you have 9 r minus 1. Okay, so because you have n minus 1, so this becomes 9. Okay, now this can be then kind of written as your r and r gets cancelled over here. Okay, so what you're left with is x is equals to 10. You take it out of the summation part because it's a constant. So r going from 1 to 10, 9 cr minus 1, 10 cr. Okay, now there is another relation when n cr can be written as n c n minus r also. Okay, so now over here you can convert this into this form. Okay, so then it will become x10 summation r is equals to 1 going to 10 9CR minus 1, and over here you can write this as 10 minus R. Okay, so n minus R, you can write it in this form. Okay. Now, what you are left with is x is equals to 10 into 19C9. Okay, why? Since n minus 1 CR minus 1 multiplied by n C n minus R would be equal to, you add the kind of the total, n that we have. So that actually becomes 2n minus 1. And then what you have below is C n minus 1. Okay. So if you multiply these two, this is the form that you can have. So 2n minus 1, so 2 into 10, 20, 20 minus 1 becomes your 19, and n minus 1, 10 minus 1 is 9. So this is what we get. So before we move forward, let's just, solve for 9C9 so we can easily get the value. So, sorry, 19C9. So now you expand it, okay, as we normally do the, kind of, how you find the coefficient. So your R is going to be 9 factorial, and this is going to be 19 minus 9 because n minus R, so that is 10 factorial. So you can write the top part or the numerator of this, combination term up to where you get your 10 factorial. So that will be 19 into 18 into 17, 16, 15, 14, 13, to 12 into 11 and into 10 factorial. Okay. So over here you can take out 10 factorial. Now this 9 factorial, okay, suppose we, kind of expand it here itself. So a lot of the terms would get cancelled out already. So let's see what we are left with. We have 9 into 8 into 7 into 6 into 5, 4, 3, 2, and there's 1 also. I'm not writing it. So from here we can start, 9, 2. Okay, so 2 can get cancelled over here. Then you have 8, then this is 2. Then you have 7, 1, 2, and you have 6, 2. Then what you're left with is 5, 1, 3, and you have one more 3 over here. So 3 and 3 can get cancelled over here. So what you are actually left with is, okay, so what you're left with is 19 into 17 into 2. Okay, so that is 19 into 34, and that is, sorry, this is not. Okay, there are a few steps that are there. Okay, so over here, what you're left with now is 19 into 17 into 2 into 13 into 11. Okay, so this is what we are getting as 19 C9. Okay, so this is what we get. So now your x, or we can just, yeah. So now your x is going to be 10, okay, into whatever was left. Okay, so you have 19, 17, 2, 13, 11. Okay, so 10 into 19 into 17 into 2 for 13 into 11 into 2. Okay, now we were asked to find the value of 1 by 1430x. Okay, so this can be now written as 10 into 19 into 17 into 13 into 11 into 2. Okay, divided by 1430. Now you can take out 10 and 1 0. So you have 19 into 17 into 13 into 11 into 2 and 143, you can actually kind of, write 143 in terms of 11 into 30. So what it does is now you can simplify this further and you will get 19, 17 and into 2. So now you will get 19 into 34 and the final answer is 646. So therefore, 1 by 1430 multiplied by the x, the expression that we had, the value is 646. Okay, so you see that, how what we used here was, different kind of rules with respect to the combination as well as the summation, kind of the concept of summation that we saw that also exists when we have the binomial expansion. Okay, so let's do another sum. So let's find the coefficient of x raised to 4 in 1 plus x squared 4. Okay, so let's method 1. Okay, so you can do this by two methods. So method 1, okay, where you will do the entire expansion and that then you can get it. So when you write 1 plus x squared raised to 4 in the binomial theorem, form, you can have 1. Okay, since the first one will be the first term, you can write as 4c0 1 raised to n, also 1 raised to 4, that will be 1, and x square raised to 0, so that will be 1 again, so we don't write it. Then the next term will be 4c1. Okay, the a part, okay, 1 will remain 1, so we will not be writing. Now x squared will be raised to now 1. Okay, now because from 0, now it will go to 1, the index of the b part, which is x squared over here. Then you have 4c2, you have x squared. Okay, so the b raised to 2. Then you have 4c3, you have x squared raised to 3 plus the last term that you will have is 4c4 x squared raised to 4. Okay, so we've reached our n. So this is where we stop. So now you can see this can be written as, so 4c0 is 1, so 1 plus 4c1 is 4 x squared. Then you have 6. Now this will be x4, x squared raised to 2, so 2 into 2, 4. Then you will have 4c3, which is again 4. And this will be x squared, raised to 3 would be x raised to 6. And the last one, 4c4 is 1. And x squared raised to 4 will be x raised to 8. Okay, so because we have to find the coefficient of x4, you can see that the coefficient of x4 is 6. So therefore, the required result is 6. Okay, so now this is kind of, where you do the entire expansion and then you can find the value. But there is another way that you can do it. So where you do not have to go into the entire expansion part. Okay, so suppose, x4, okay, x raised to 4. Now we already know that part of the power of the x is squared. Okay, so this is constant. So x squared is already going to be there. Okay, so that should be multiplied with another term. Okay, so that term will depend on the r that we take of the binomial expansion. Okay, so this you can write as x should be raised to 2r. Okay, so over here you can see that this means that 2r should be equal to 4 and therefore your r is going to be 2. If your r is going to be 2, we need to find the coefficient of the third term. So that is T3. Okay, so where your r is your 2. Now when your r is 2, your n CR becomes 4C2. Okay, and you will have A raised to 4 minus 2. Okay, over here A is 1, so let's not write it. So then the next one is the B raised to R. Okay, so your B is going to be x squared and raised to R, so that is 2. Okay, so now we only need to find the coefficient. So the 4C2, as we know, is going to give you 6. So this is easy in the sense that you only have to figure out the which term it is. Okay, what is going to be a R, the respective R, and then you can find it. Okay, so this is how you can solve such terms. Okay, so either you such examples. So either you can do the entire expansion, okay, or you can do directly you can solve for the term. Okay, so this is comparatively easy for us to understand that. Okay, so let's do some more examples. Okay, so suppose the coefficients of three consecutive terms of 1 plus x n plus raised to n plus 5 are in the ratio of 5 is to 10 is to 14. Okay, so the first part of the sum would be find n. Okay, and the second part is the find the coefficients. Okay, so suppose we are given in this kind of a question. So over here to easily calculate, what we will use is the entire form of the general term. Okay, so general term for binomial theorem or expansion. Okay, so binomial theorem is T R plus 1, okay, is equals to N T R x raised, or A n minus R B raised to R. Okay, so in case of when we have given we have 1 plus x raised to n plus 5. Okay, so over here your n is n plus 5 and your a is 1 and b is x. So therefore your t r plus 1 can be written as n plus 5 c r. So a is 1, so anything anything 1 raised to anything actually would be 1 itself, so we are not going to write it, and b would be raised to r. Okay, so this is what we know. Now if you take n plus 5 cr as the middle of the three consecutive terms, okay, as the middle term of the three consecutive terms, so what we can write is the n plus 5 cr minus 1 and n plus 5 cr plus 1 are the three are the coefficients for the three consecutive terms. Consecutive term coefficients. Okay, so this is what we are going to get. So now as for the, it is given then that your n plus 5 cr minus 1 ratio with n plus 5 n plus 5 cr ratio with n plus 5 cr plus 1 is 5 is to 10 is to 14. Okay, so now let's take different ratios. So the first ratio that we can take is n plus 5 CR upon n plus 5 CR minus 1. Okay, so this would be 10 by 5. So this you can write in terms of the, you can get the factorial form of this NCR and n plus 5 CR and n plus 5 CR minus 1. So that you can then write as n plus 5 factorial upon r factorial n plus 5 minus r factorial, okay, divided by n plus 5 factorial again, and then you have r minus 1 factorial over here, and now you have n plus 5. Okay, so if you have say n minus r factorial and your r is r minus 1, so this actually becomes minus r minus 1 factorial, and then you will get this n minus r plus 1 factorial. Okay, so this will be n plus 5 minus r plus 1 factorial, and this will be equal to 10 by 5. Okay, so over here you can see that n plus 5 factorial will get cancelled. Okay, and r factorial you can actually write it as you can write r into r minus 1 factorial, okay, multiplied by n minus plus 5 minus r factorial divided by, actually this would be 1 divided by, okay, and you have cancelled out n plus 5 factorial, and the next would be r minus 1 factorial, and you keep this as it is over here, so you have n plus 5 minus r plus 1 factorial. Okay, so this would be equal to 10 by 5. So over here again you can see you can cancel out r minus 1. So what you finally get is n plus 5 minus r plus 1, okay, factorial divided by r n plus 5 minus r factorial is equals to 10 by 5. Now over here again you can write your n plus 5 minus r plus 1 factorial as n plus 5 minus r plus 1 multiplied by, now obviously there will be a decrease of 1 in the factorial form. So if you put minus 1 over here, so your plus 1 minus 1 gets cancelled. So what you get is n plus 5 minus r factorial upon r into n plus 5 minus r, okay, factorial, that is equal to 10 by 5. So again this and this will get cancelled. So what you are left with is, okay, what you are left with is n plus 5 minus r plus 1 upon r is to 10 by 5. Okay, so if you now reduce this in, or simplify it, you will find you get n plus 6 minus r 5 is to 10r. So this will actually give you n is equals to 3r minus 6. Okay, so let's take this as your first statement. Now, what we will do is we will take the second ratio. So what is the second ratio that we have is n plus 5 n plus 5c r plus 1 upon n plus 5c r is equals to 14 by 10. Okay, so this can be written in terms of the factorial way. So n plus 5 upon r plus 1 factorial, n plus 5 minus r minus, okay, 1 factorial. Over here, why? Because if we have n minus r and over here your r is r plus 1, so this becomes n minus r plus 1. Okay, and then what you're left with is n minus r minus 1. Okay, so that's why this is what we get in the denominator, and this would be divided by n plus 5 factorial upon r factorial n plus 5 minus r factorial, and this will be equal to 14 by 10. Okay, so now if we simplify the left hand side, we will get, that's right, it will form factorial upon r plus 1 factorial n plus 5 minus r minus 1 factorial multiplied by r factorial n plus 5 minus r. Okay, so let's just solve the LHS part first, so it will be easy for us. Okay, r factorial upon n plus 5 factorial. So n plus 5 again gets cancelled. Now over here, you can write r factorial, okay, in the form as n. You can actually, expand your, you can keep your r factorial on top, and you can also make, you can get the next term of this factor of n plus 5 minus r. So there will be minus 1 here. So this actually then becomes n plus 5 minus r multiplied by n plus 5 minus r minus 1 factorial. Okay, divided by, so you have r plus 1, you expand that. So you have r plus 1 and then again r plus 1 minus 1 as we go into the factorial form. So that would be r factorial itself. Okay, and then you have n plus 5 minus r minus 1 factorial. So this will get cancelled and r factorial gets cancelled. So the LHS part comes down to n plus 5 minus r upon r plus 1. Okay, so you input this over here. So what you get is, therefore, n plus 5 minus r upon r plus 1 is equals to 14 by 10. Okay, so now you have 5n plus 5 minus r multiplied by 7r plus 1, and that way you get as 5n minus 12r plus 18 is equals to 0. So this is your second statement. Okay, let's just add a slide. Okay, so our first statement was n is equals to 3r minus 6. Okay, and the next one is 5n minus 12r plus 18 is equals to 0. Okay, so putting 1 in 2, what we get now is 5 into 3r minus 6, okay, minus 12r plus 18 is equals to 0. So you get 15r minus 30 minus 12r plus 18 is equals to 0. So you have 3r minus 12 is equals to 0. So therefore your r is equals to 4. Okay, so if your r is equals to 4, so now when you have n plus 5, okay, so with your r, you can calculate your n easily. So now your n is equals to 3 into 4. minus 6. So that is going to be 6. So n is 6. So now your coefficients, what will your coefficients become? Okay. So your coefficients will now become 6 plus 5. Okay. So your n is equals to 6. So we found our first result. Okay. 1 n is equals to 6. So now what is the second part? Find the coefficients. So what are the coefficients? So you have 6 plus 5 c r plus minus 1. Okay, so 4 minus 1 was one coefficient. Then 6 plus 5 c r is 1. Okay, and the next one will be 6 plus 5 c 4 plus 1. Okay, so this is what 11 c 3, 11 c 4, and 11 c 5. Okay, so if you calculate them, so you have 11c3, so that would be 11 into, so this would be 3 factorial multiplied by 11 minus 3 is 8 factorial. Okay, so you just write into 9 into 8 factorial, so 8 gets cancelled, 3 ones are 3, 5, so you have 15. So this will be 165. Then you have 11c4. So you write 4 factorial, 4 into 3 into 2. And 11 minus 4 is 7 factorial. So 11 into 10 into 9 into 8 into 7 factorial. So this gets cancelled. 4, 2, 2, 2, 3, 3. Okay, so this is 30. 30 into 11. Okay, so that is 330. And the last coefficient that we have is 11c5. Okay, so that would be 5 into 4 into 3 into 2 multiplied by your 5. 11 minus 5 is 6 factorial. So you have 11 into 10 into 9 into 8 into 7 into 6 factorial. So this gets cancelled. So 5, 2, 2, 2, 3, 1, now 3, then 4 into 2. So you have 6. Okay, so you have 6 into 7, and 6 into 7 is 42, and you have 11 into 42. So that would be 462. Okay, so the second part of it that we have to find the coefficients. So the coefficients are 165, 330, and 462. Okay, so you can see that it's easy to solve such questions if you know the rules. Okay, and if you know the how to write the general term and how you can do the combination concept also. So we will stop here today. So hopefully this has helped you, and we will carry on with the other parts of the binomial theorem and also solving a few more examples in the next class. Thank you.